So next we're going to look at the titration of a weak acid with a strong base. So let's consider the titration of 25 milliliters of 0.2 molar hydrofluoric acid with NaOH. So we know that they react according to the equation. NaOH plus HF will yield water and sodium fluoride. So we know that the equivalence point is reached when the number of moles of base added is equal to the number of moles of acid that are initially in the solution. So to start out, we need to figure out what the initial moles of hydrofluoric acid are. So the moles of hydrofluoric acid will equal 0.025 liters times 0.2 moles per liter. This is just using 25 milliliters converted to liters multiplied by the molarity. This should give us 0.005 moles of hydrofluoric acid. Now we need to find the volume of NaOH. So we take the 0.005 moles, but instead that'll be moles of NaOH based on the stoichiometric ratio because it's 1:1. So in this case 0.005 moles of NaOH. We'll convert that using our molarity. This should be 0.2 molar sodium hydroxide. So 0.2 moles per liter will give us 0.025 liters of sodium hydroxide that will be added. This will be at the equivalence point. So now let's take a look at what happens when we add, say, 10 milliliters of sodium hydroxide. That'll obviously be less than the equivalence point. So for 10 milliliters of sodium hydroxide, we're going to use our BAA table. So OH minus plus HF will yield H2O plus F minus. Water doesn't come into play because it's a liquid. And so firstly we need to figure out how many moles of HF are added. Or excuse me, how many moles of OH minus are added to the solution. So we're going to take 10 milliliters converted to liters and then multiplied by the molarity. This should give us 0.002 moles of sodium hydroxide that are added. So at the start, we have 0.005 moles of hydrofluoric acid, which we found earlier. And to that, we are going to add 0.002. We subtract to get 0.003 moles of hydrofluoric acid, and that reacts to get 0.002 moles of our F minus. So then we use Henderson-Hasselbalch equation, pH equals pKa plus the log of the concentration of the base over the concentration of our acid. So to find the pKa, we're going to take the negative log of our Ka value. Now before we started this, before you start this problem, you're going to have to look up what the Ka value of hydrofluoric acid was in the book. I've already done this for us, so we know that 3.5 times 10 to the minus 4 should be the Ka value for hydrofluoric acid. We add the log the concentration of base over acid, which is 0.002, from the base, which is F minus, divided by 0.003 for the acid. This will give us a pH equal to 3.28. Now this is what we expected. The pH should be lower than 7, or lower than what the pH at the equivalence point will be, because we haven't added enough base to overcome the acid just yet. So for the next part, let's take a look at what happens when we reach the equivalence point. So 0.025 liters of sodium hydroxide are added. So 0.025 times 0.2 moles per liter, which is our molarity, gives us 0.005 moles of NaOH that is added. Now we know that all of this should be converted to our F minus, which is our base, during the reaction. So we can say that the concentration of F minus equals to 0.005 moles over the total volume of the solution, which is 0.025 liters plus the initial 0.025 liters. And you calculate that, which should be about 0.1 molar. Now since we're working with molarities, we're going to use an ICE table. So initial, change, and equilibrium. So F minus plus H2O react in equilibrium to form HF plus OH minus. Water, again, is not a player because it's liquid. So we had 0.1 molar F minus. This is about 0 and about 0 over here. So the change, since we don't have any coefficients, it'll be minus x, and plus x. To get 0.1 minus x, and x. So in this case, since we have F minus, we're actually going to be calculating a Kb value. So in order to find that, we know that Kb equals Kw over Ka. The Kw will always be 1 times 10 to the minus 14th at 25 degrees Celsius divided by our Ka, which we saw earlier, to get 2.86 times 10 to the minus 11 for our Kb value. So based on our reaction from here, we know that our 2.86 times 10 to the minus 11, which is our Kb value, will be equal to the concentration of the products over the concentrations of the reactants. This will give us x squared over 0.1 minus x. Since we have a very small Kb value, we're going to assume that our x here is small, which will give you that x squared is equal to 0.1 times 2.86 times 10 to the minus 11. Then you take the square root of both sides to find your x value. So we find that x equals 1.69 times 10 to the minus 6. Now it's important not to forget what the x actually stands for. We remember that x stands for the concentration of OH minus. And therefore, we know that Kw is equal to the concentration of H3O plus multiplied by the concentration of OH minus. We can use this to calculate the H3O plus is equal to our Kw over the concentration of OH minus, which gives us a value of 5.92 times 10 to the minus 9. Again, we use our equation that pH is equal to the negative log, the concentration of H3O plus, and we find that the pH equals 8.23. Now this is at the equivalence point. We know that since we're using a weak acid and a strong base, it should be known that the pH will be above 7. It'll be more basic because we did use a strong base. So we can assume that when we add more base, the pH value will be greater than what it is at the equivalence point. I've already worked out some calculations for this. It's very similar to what you would do in the previous problem when we did strong acid, strong base, and the one that we did when we only added 10 milliliters of NaOH solution. Overall, you're going to find that the pH is about 12.52, which is what we expected.